हम जो है खुद स्टूडेंट थे आज से कोई 30 साल पहले एनईडी में. तो I just wanted to make sure that if someone can actually do a proxy, what I mean is कि कोई attendance sheet अगर आप लोग circulate कर लें और सोहेल उस्मानी साहब को at the end of this lecture जरूर दे दीजिए उन्हें, ताकि हमें पता हो कौन से स्टूडेंट्स अटेंड कर रहे हैं और उनको हम फिर सर्वे भेजते हैं ताकि उससे हमें अंदाजा हो कि हम आप लोगों को क्या चीज पसंद है या क्या चीज आप सुनना चाहते हैं. I just want to make sure that that happens. So who's going to take the responsibility for that? Can I get a name for that?
I'm Tarun Wafal and executing this program. I have been assigned.
Thank you. So Tarun, if you can actually start that, that would be great. And I can now see the students also. Thanks a lot for putting the camera on. Assalamu alaikum, everyone. So today we are going to have a talk on Introduction to Systems Thinking. This webinar is actually, the main speaker on that is Dr. Abbas Zaidi. I also have my colleague Asma Ali on the phone. She actually helps us set up these calls. Today's speaker actually is from George Mason University in Virginia. He's a professor at the Department of Systems Engineering and Operations Research. Dr. Zaidi also is associated with the Architecture Lab of Systems Engineering at the university, besides being a full professor in electrical engineering. Before this, Basa was in Karachi. He actually was at the Muhammad Ali Jinnah University. He was an associate professor and the dean of faculty in the Department of Electrical Engineering and Computer Science. And prior to that, he has also served as an assistant professor at University of Karachi. And of course, he is an alumni of an NED University and in electrical engineering. And after that, he has also pursued his master's and a PhD from George Mason University. Abbas Saab, this is over to you now. And thanks a lot for your time in the morning.
Thank you. Assalamu alaikum, everyone. This is Abbas Zaidi. I'm sorry, Arif Sattar was talking to. Mr. Arif Sattar has already given a brief sort of an introduction. I really do not like to be introduced. But I need to give you sort of my academic background in terms of where I'm coming from, so you have a clear picture as to what it is that I'll be presenting today. I'm assuming that most of you are from civil engineering department. If I'm not, right in my assumption, please let me know. In any way, what I've done is I've prepared a sort of more of a motivational talk, an introductory orientation of an area called systems engineering, especially the kind of thinking required to solve problems or when it comes to the way system engineers do their job. So let me give you a brief sort of an introduction or background of my professional career. So you have heard what I've done, the kind of degrees and the kind of institutions that I have been associated with. By training, I'm an electrical engineer. I did my undergraduate and all my graduate degrees in electrical engineering. And since 2001, I'm more interested in solving problems that are considered systems engineering problem or systems problems. So my background is in electrical engineering, but currently what I do is systems engineering. So I thought that I should talk about some of the things which I have been doing for the last 10 years and the kind of issues that people struggle with or they do when they are considered system engineers. And the classes that I teach, I have seen a large number of students with different backgrounds uh, now coming to system engineering departments for their graduate degrees. The class that I'm teaching right now, half of them have system engineering background, but the remaining half have students from computer science, electrical engineering, and civil engineering. So I thought that it may be of some interest to those of you who have civil engineering background or any other background. I'm assuming that any university does not have a systems program. When I got admitted to NAD, there was a program that started the same year. It was computer systems, but that's not system engineering that I do over here at George Mason University. So I like to give you an overview of this area. There will be very little technical content in my presentation, in my talk today, since I did not know what background the students are coming from. So it was, I thought that I should give something which may be relevant for all the students coming from all the backgrounds or all the disciplines that you have at NAD University. So let's go and talk about the topic, which is Introduction to Systems Thinking. So I'll give you some definition to sort of have a common vocabulary, common language between us. So if I use a term, we don't have any confusion about it. So when it comes to system engineering, a system, again, most of the definitions are exactly same, no matter what discipline you are coming from. But I thought it's good to have a quick sort of a refresher of all those definitions before I start using those. So a system in system engineering or any other engineering is a collection of elements. Those elements may be hardware, software, people, facilities, and procedures organized to achieve some agreed upon purpose or purpose. So the idea over here is that you have certain objects, certain elements, and they are organized. For example, in your lecture hall, there are many things which are there. So the moment a person comes in, sees all those chairs and the screen and all the equipment that you have up front, the way that these things are organized, anybody can guess or predict that this, there is a function of this room or there is a function behind this organization. You put all these things in a storage, you have exactly the same thing, but the way they are stacked over there or organized over there would tell a person that the function of these things is, is just to be stored, and it's different from when you see exactly the same elements, same software, hardware, people in a lecture hall. So it's collection of elements, and the elements could be anything. They may be people, and the important thing is that they are organized in such a way that there is some purpose behind this organization, and there's a function behind this sort of a collection. And engineering is a discipline for transforming scientific concepts into cost-effective products through the use of analysis and judgment. That's what we do. That's what NAD teaches us to do as part of professional engineering. When it comes to engineering a system, again, it's the same principle of engineering that we apply. It's a discipline that develops, matches, and trades off requirements, functions, and alternate system resources to achieve a cost-effective life cycle balance product based upon the needs of the stakeholders. So, this is just a sort of a quick definition. I'm not going to sort of go into the details of these definitions. Just to refresh, our memories as to what is it that we, do as part of our engineering. The important question is why engineering a system? Why is it that system engineering is so important? And this is a figure that I've taken from a professor at University of Southern California. What is important about this is basically you look at the x-axis, there are different stages of engineering a system. So it's basically a life cycle of a system engineering design. So you start from conceptual and preliminary design, then It is followed by a detailed design and integration. Then you start constructing or producing the thing. You use refinement and disposal. So these are different stages. Again, I'm not going into the details of all the stages that people have suggested or they basically proposed. Just a sort of a quick step by step or different steps which are involved in a life cycle of a product that we may be developing as part of our job, as part of our profession. Okay. What you see as these two curves over here, the one which says cost committed and the other which says cost incurred. The important thing is that if you look at this blue ball that shown up on this graph, that this is the phase or step where somebody has done the detailed design and integration. And at this stage, in general, and again, this has come from analysis of several system engineering projects that this author has looked into. The 20% of the total cost has incurred so far, but it affects 80% of the total cost that will be incurred as part of this project. So what it says is that the first few phases of a system design and a product design, although it requires hardly 10-20% of the total cost, but it affects 80 to 90% of the cost, which will eventually be incurred as part of this product development. All it says is that the initial phases, although they are not very costly, you don't spend too much, but whatever is it that you do in that phase affects a large portion of your budget that is allocated to this project. All it says is that if you do not do your job right at this early stage, when you are doing only 20% or spending 20% of the total budget, you may have cost overruns, you may have wrong estimates for the completion. So it's very important that we are very careful for this early stage of conception, the preliminary design, the detailed design and integration, where we haven't yet started constructing or producing or creating the product that we are supposed to be creating. So what happens usually in the Western world, that when we have these cost-cutting measures, they usually affect this initial phase. So again, you cannot cut any cost when it comes to actually building something. If you are civil engineer, if you are building, for example, something, there is hardly any room to cut cost when it comes to the actual material, actual building cost. So what happens is that people try to cut costs from these initial phases. Try to involve less people when it comes to the conceptual and preliminary design. They try to go very quickly over the initial phases because that's the only portion where you can cut costs. But what happens as a result, that since the effect of these initial phases is a lot on the total cost or the total estimates or the total timing estimates of the project, they then run into problems, cost overruns, projects do not finish on time and all those things. So it's very important that we pay attention to these initial phases, and that's where system engineers actually do their job. So all I'm trying to convince you over here is that what systems engineers do may not be the actual construction or production of something that actual engineers or other engineers, electrical engineers or civil engineers or mechanical engineers may be doing. But what we as system engineers do affects, the actual development of the product on time within the budget and all the other constraints that we may have. So that's the major reason why system engineering is important, because it eventually affects the overall health of the project. Here is again the same professor from USC came up with these figures These are comparison of relative cost to fix software projects. So the figures are sort of estimated from looking at certain major software projects. But these things can also be applied. The figures can also be applied to just about any project, be it software or any other complex system, which may involve software, hardware, and people components. So all it says is that if you have, I'm just reading the first row of this table. So if you have, let's say, requirements, and there is a problem found at the requirements stage, and if it costs, let's say, $2, and what you see, 1 comma 3, just the range, so plus minus $1. So if there is a problem and you find it at the requirements phase, and if it takes $2 to be fixed, the same problem is identified at the design phase, it will cost $5. So these numbers are relative. I'm not saying that it costs actual $2. All it says is that if it, the first one, if the fix at requirement phase costs 2, it will be, the cost will be doubled if the same problem is found and tried to be fixed at the design phase. Look at the maintenance phase. If you try to fix the same problem at, when you are sort of, when you have deployed the system, you are just maintaining it, it will be comparatively, 100 times larger than the cost at the requirement phase. So it's better to find those problems, it's better to fix them early in the process. So all these figures tell us that if you find something at a requirement phase, it may cost you very little. If you find the same sort of a problem and try to fix it at coding phase, it may be 5 times more expensive because it says 10 over here. And if you try to fix the same problem at maintenance phase, it will cost you $200 compared to just $2 at the requirement phase. So all it's trying to convince is that find the problems first, try to fix them as early as you can, and that's what systems engineers do. The actual problem and the fix of that problem will be done by the engineers from the background that this problem comes from. So if it's a mechanical engineering problem, mechanical engineers would be doing it. If it's a software problem, software developers will be fixing that problem. But identifying it and have people to fix it, that's what system engineers do. So system engineering is a process that is comprised of, like any engineering, it has many processes that people follow to do certain things. So if I try to define system engineering, it's a process that is comprised of a number of activities that will assist in the definition of the requirements for a system. So you get requirements from stakeholders, from customers, from users, transform this set of requirements into a system through development efforts, and provide for deployment of the system in an operation environment. So a system engineer basically is required, is needed, or in this country, for example, USA, are basically tasked to look after all these phases in the life cycle of a system design. There are two major perspectives or roles that a system engineer is supposed to do. A system engineer takes a process-oriented view of the efforts needed to see the system. That's exactly what any other engineer do. We have certain processes in place, or a system engineer is trained to basically follow certain processes when he or she does his or her job. But a system engineer is more than a sort of a project manager or a process monitor. A system engineer is also is an integrator. So the needs of the customers, the system production team, the existing legacy systems which you may be employing as part of your design are all sort of there for a system engineer to integrate and to look after. So the system engineer does not just do his or her job, but is also involved in the jobs of other engineers, which are part of this large team of engineers. So the function of system engineering is to guide the engineering of complex systems, and uh, and the question some people might have in their minds is, okay, so what is the difference between an electrical engineering or a mechanical engineer or civil engineer, or for that matter, any other um, engineer? The difference um, is that a system engineer is not focused on just one aspect of the system. So if you are a civil engineer, you may be interested in the only that aspect which comes under your jurisdiction. An electrical engineer may only be interested in his part or her part of the total project. A system engineering, as part of his or her job, is focused on the system as a whole, which may include electrical systems, which may include construction of things, physical things, or any other uh, uh, engineering discipline. The system engineer also leads the formatting concept development stage. These are the two early stages that I talked about on the graph. The early ones, which are not very costly but have a very costly effect on the overall project. And a system engineer bridges the traditional engineering discipline. So system engineering is also tasked to bring together all the other engineers and talk to all the engineers so that the system as a whole can be constructed. So a system engineer, I'm sorry, a civil engineer may tell someone that this is not my job. This is beyond my training, or this is not a civil engineering job. An electrical engineer may say the same thing, but a system engineering may have to know all these things to bring all these things together, to be able to talk to all engineers, civil, electrical, mechanical, and bridge the sort of the language barriers or the discipline barriers that exist among all these different systems, all these engineering disciplines. So there are some sort of system engineering challenges that I try to outline over here. Again, system engineering is not new. In early 40s, 50s, we had hardware-centric system engineering, the industrial sort of age, large machines, huge automation when it comes to the developing things that we human beings were developing. At that time, the issue was hardware centric systems that we were developing, large machines, large industrial complexes, and the human was just a user or an operator of those large machines. So the issue at that time were considered man-machine systems. So we addressed human in that era to man-machine system work. So if you look at the literature, you will find lots of material on man-machine interfaces, man-machine systems, and these are the terms that you can Google and find lots of literature coming from that era. Okay, in 60s and 70s, we progressed to software-centric systems, and again, the human being was addressed to human-computer interface work. So HMI and all those terms that you hear, they came from that era, 60s, 70s, and 80s, when we had large-scale systems, large databases, software-centric systems, and the issues that people discuss in systems engineering. Or areas which are considered system engineering areas, human computer interfaces and all. At present, we are now into an era which is considered human-centric system engineering era. So what we have right now are basically three dimensions: hardware, software, and human. And system engineering is basically looking at issues with systems which have these three different dimensions. So we have hardware systems, we have software systems, and we have humans, not considered as things or elements or components outside the system. They are part of the system. So human in the loop kind of approaches that people are looking at. So when it comes to hardware humans, we have man-machine systems. When it comes to hardware software systems, we try to look into issues of how hardware and software can be integrated. The software and human aspect is covered by human-computer interfaces or human-computer work that people have been doing. So what you see right now in this era is basically is a much broader context in which system engineers work. So we have all these three components sort of covered or studied as part of system engineering. So since you have these three different components that comprise our human centric system, the challenges are that traditionally, since we have been developing hardware and software centric systems without a regard of a human being as someone who is part of the system, the human being was always someone outside the system. We focus too much on hardware and software integration, and the rest was human beings. Once we have a system, the human came afterwards. So we had to invest a lot in training. How do you train people to work with those large hardware and software systems? So the challenge nowadays for system engineering is that instead of keeping this human out of this sort of loop until we have the system commissioned or deployed in the operation environment, we keep human being as one of the several components or elements that make up this whole system, and we try to solve the problem right there and then as to how these human beings will be interacting with this hardware and software or hardware and software that make up our system. So this is the challenge nowadays in system engineering. How do we basically develop systems where we have all these three different components, and we basically have a human-centric approach of developing those systems. We want to have a human being who is not just a user of this hardware and software that we have in the system, but is also a component of that system. Which brings us to the issue of interfaces. So how do we design interfaces which are human-friendly, for example, and how do we basically allocate tasks among these three components? If I'm given a system to design, what are the functions that will be done by human beings, what are the functions that will be done by hardware, and what are the functions that will be done by the software. So it's an interesting sort of a decision to make when you have a complex system to develop, because there are many things that both hardware and human beings can do. So how do you decide which of those functions can be done by or should be done by hardware? What functions should be done by human beings, and we should keep hardware outside that boundary. Again, and there's a long list of challenges, so I try to come up with some which are, to me, are more interesting than others. Then we have this issue of some very interesting systems that we call system of systems. So these are systems, and what you see on this slide at the bottom are just two pictures that try to describe the way we look at how we combine existing systems into larger systems. So on the left-hand side, we have all the nodes in this graph are apparently different systems. There may be software that are already out there, and there may be other physical systems. So we may have an example. For example, you may like to develop a crime sort of a control strategy or a system that looks into crime in a society. You may already have certain databases like Nadra in Pakistan, which has a very extensive record of all people, their biometrics and all those things. And you already have the law enforcement agencies in place. So you have different systems already in place, and what you are trying to do is to put all these things together in a way that solves a problem, that serves a purpose. Okay, so you already have different systems, and the pairwise integration or the monolithic approach, what it does is it basically puts all these systems together in a structure as if you are constructing a new system with its new, policies of integration and how these different systems will be talking to each other. And it's basically a strongly coupled integration. So they are forming a new organization. Their previous identity is now gone. So this is one way of constructing a new system. The system of systems, on the other hand, is a new way of constructing or designing systems where what you do is you bring in new systems, but they are autonomous systems. They can come and leave your sort of federation or the collection that you are developing over. So you may, for example, find a need for a system that already exists. For example, Suparco has some satellites up there, and you may be interested in getting some information from those satellites. You may be doing some, let's say, disaster relief work. And so for this new disaster relief system, you may require help from the satellites which are under Suparco's control. You may need help from some NGOs, let's say, who have offices in that area where you may be working. You may need some technical help from some other organizations which have some disaster relief expertise or may have equipment that you may require. The system of system approach looks at these new systems not as highly or strongly coupled new organizations. Rather, it looks at federation of autonomous systems which already exist out there. They have a function to perform. They have a purpose for their existence, but they do not lose any of those functions and purposes. They come into an organization, they come into a federation, they do their thing, and then they may leave whatever they like. So system of systems is a sort of a new way of developing new systems where the component systems are themselves systems. They are out there, they are already working. So I have some examples of some system of systems that I'll show you towards the end. Here is since I talked about a system engineering process, here is a sort of a broad diagram that shows a very oversimplified sort of a sequence of things that a system engineer does. But I'm not interested in going over these steps because that's not the topic that I like to present. The important thing is that whatever is it that I have described so far, a valid question may be, so what are the expertise required of a system engineer, or if I have a system engineering team, what are the different expertise that a person would like to have covered by these people. So here is again, not a comprehensive list, but some of the things that are required, expected of an SE team or a system engineering team. You must have domain information. You must be able to get the requirements from stakeholders. You must have management skills. And that's why I've seen some of the students in my class who may have gone to business schools for their MBAs, but now they are basically, instead of going for MBAs, they are going to system engineering graduate programs and getting a system engineering master's degree, because that's where they see some of the same management material. Again, in a different context for a different purpose than what business schools traditionally offer. The SET must have people which are well versed with system engineering processes. So we have, like any other engineering, certain methods to follow, and the team must have people who know what those methods are and must have experience applying those methods to system engineering problems or product development problems. We should also have, as part of our SE team, experts in the relevant technology, so different engineering disciplines. So if you are building a bridge, you need civil engineers, mechanical engineers. And if you are building, for example, something that requires electrical engineers, chemical engineers, those engineers must be part of this system engineering team. They may not be able to talk to each other, but that's the job of this entire team to basically develop an ecosystem, if you will, where engineers from different disciplines can basically contribute and talk to each other to solve a system as a whole. Finally, we also need people from modeling, simulation, and analysis. That's my subject when I teach courses in system engineering department. These are the sort of things that I do. So we need to have people who can model systems, simulate them, or in any other way analyze those systems. We don't want to build systems and then realize that something was wrong or there were certain requirements that the system cannot meet. So we basically are always in search of ways of having some prototype, some analytical artifact of our future system or the system that we are building or the product that we are building, so that we can analyze it, simulate it, if it's a dynamic system, and see if we can find some problems with the system design and fix those before we start building it. And remember that graph, which shows that if you delay your fixes, they cost you money, a lot of money if you are late and haven't find. Okay, system engineering, as I mentioned earlier, is not new. I gave you some examples from last century, 1940s and 50s. It's even older than that. Remember pyramids in Egypt? Again, if you ask a system engineer would say, "This is what the system engineer must have accomplished." The construction did not only involve the civil engineer, if you will, of that time, but it also involved project management. There were so many slaves, and their families, there were health problems, there were animals that they brought from different parts of the world who can carry those large stones. They brought stones from other parts of the world. So it was a huge undertaking with social, political considerations, human considerations, and many others. The animal consideration, if you want to, because there were so many animals which were used to push these stones up these pyramids. So it was not just sort of a civil engineering job, if you like to take the credit. It was a lot more than that. We can compare the building of pyramids to the Big Dig in Boston, which has been completed in 2007, where they basically dug up the whole, city. They basically were trying to build a tunnel in the downtown. It was, I guess, 3.5 meters long tunnel that they had to dig up, and it was a huge undertaking. There were all kinds of engineers who were involved, mechanical, civil, environmental issues were there that they had to look into, political issues that they had to resolve, and this is a very interesting also example of doing things not the right way. So it started in 1982. It was supposed to be completed in 1998. It took almost a decade longer than the initial estimated time, and a lot more money was required to finish it. If you ask a system engineer, the system engineer will tell you that the reason behind all these cost overruns and delays were caused because of poor system engineering. So all the other engineers were doing their job, but since the initial phase was not done correctly, they had to pay more. They had to wait a lot more before people can use those funds. Here are some examples of system of systems. The U.S. Coast Guard deep water system, again, it's not something which has been deployed, but it's just a concept picture that I show you over here. It shows different agencies, different platforms, different assets belonging to different organizations used uh, in support of what the future U.S. Coast Guard will be doing. So it has certain satellites, certain other offshore, onshore systems which are employed to uh, do what U.S. Coast Guard does. Look after their coastal areas, uh, identify different kinds of smuggling activities and prevent. Then we have this another example. Again, it is a concept so far. Next generation air traffic management. It's called next gen. The idea over here is to move from the current radar-based air traffic uh, management system to a system which will be using radars, satellites, um, carrier-to-carrier communication. So what you see over here is basically a new concept where the information will not just come from the fixed radars, which are in control of FAA, but there are many other sources or sensors which may belong to other organizations or other agencies, and they all basically contribute to manage the air traffic in the United States. So it's a system of systems because you do not have a single organization or a single entity controlling all the assets that contribute to this system's function. And the issues are how do we bring all these organizations together, their assets together to do the function required of this new system. And there are many issues in this. If you have everything under your control, you may still have problems, but they are under your control. But if other organizations own those assets or those components, how do we make sure that we get the job done? So, as a result, what we have is a situation where the systems are more and more complex. As part of system engineers, as part of our education, the method and the process-oriented approach, we do step-by-step analysis like any other engineer. But this step-by-step analysis is all good and suitable for low-dimensional complexity. What we have been observing as system engineers is that as the complexity increases, this step-by-step analysis actually breaks down. The engineers, as part of their training, are sort of taught or trained to divide and conquer. What we do is we break a system into smaller systems, we develop them, and then we put them together. But there is a growing realization among our community, system engineers, or any other community, who deals with large and complex systems, that cutting these systems into smaller ones may not be the right thing to do, because what happens is when you break the system into smaller ones, you basically destroy the connectedness between different components of the system. Assuming that if I tweak the system at one sort of part and hoping that it will not have any effect on the others may not be the right assumption. So the realization is that we should, change the approach. We should study the system as a whole. So as complexity increases, the approaches that we have learned, the methods, the methodical, analytical skills that we have acquired as part of our education, they become overwhelming. They don't work. And what we are left with is basically an approach that is called, a tunnel vision, or what we do is we develop a stovepipe system. These are some of the terms that you hear a lot in this part of the world. So what we do is we try to close our eyes from all the other things that are difficult to sort of grasp using the methods that we have learned. So we try to oversimplify things at times, and in the process lose the overall vision. So that's a serious challenge to system engineering. The solution to this problem, if you ask people, they will tell you that there exists none. So we do not have anything at present. There are many frameworks that have been proposed, to how systems can be designed and developed. You hear terms like system architecture and those, where they try to come up with blueprints or designs of things which capture all aspects of a system using different modeling languages. But still, it's something which work in progress. The idea over here is behind all these efforts is that it's both an art and a science. We must develop a different way of seeing a system. Success in any endeavor is first and foremost a matter of accurate seeing. If you do not have a good grasp of what you are doing, you do not really know what problem you are solving. So this is basically a departure from the linear thought that we are trained to exercise as part of our training in engineering. What we are going towards is a cross between artistic and scientific reason. So that's what to me is something very interesting in system engineering and in any other engineering discipline. We basically follow the same step by step, the linear thought. You do this thing first and then you do something else. But in system engineering, what we are looking for is a departure from this way of doing things. So in a system engineering environment, solving a problem may require seeing exactly what the problem is and then imagining the system and the problem. And this is where it's different from all other disciplines. You don't imagine a problem or a solution in any other discipline. In system engineering, the emphasis is to imagine the solution to a problem. So the idea here is that with your eyes, you see what is not working, you make it work in your mind, and you simply have to identify the difference. Okay? So it's basically learning to see the complex is what we try to do. And there are many, proposals or approaches that people have come up with. So what I try to give you is sort of an introduction to a different kind of thinking that people are promoting in system engineering, and see if it interests you or not. So what it says is that we need a more holistic approach than an analytic one. We need to go from an L mode to an R mode thinking, and I'll explain what L and R modes are, or a better blending of the two. So what you see in system engineering is a theory called whole brain thinking, or a thinking which requires both L mode and R mode. What are these L and R modes? Let me very quickly go over these things. And I'm almost towards the end of my presentation. The people who study human brain, they basically tell us that the two hemispheres that we have in our brain, they have two totally different functions that they perform. We have the left part of the brain and the right part of the brain. And that's where these L mode and R mode come from. So the left brain functions are listed over here. So if you are responding to verbal instructions, it's your left part of the brain which actually is doing that. The left part solves problems logically and sequentially. It looks at differences. It's very planned and it's structured. It prefers established expected information, prefers talking and writing, prefers multiple choice tests, control feelings, prefers rank authority structure, sees cause and effect, is a splitter, distinction is important, draws on previously accumulated organized information. So that's what the left part of our brain does. And again, I'm not a biologist or a neuroscientist, but that's what the people who study human brain have been telling us. On the other hand, the right side of the brain performs slightly different functions. It responds to demonstrated instructions compared to the verbal instructions. So, if, for example, if you are not good at looking at demonstrations and learning from those, learning from examples, it may be the problem of the right brain, not the problem at the left brain. So, if people do not stop at traffic lights in Pakistan, that's the right brain problem. Okay. Similarly, the right part solves problem with hunches, look for patterns, look for similarities, is fluid and spontaneous, prefers elusive, uncertain information, prefers drawing and manipulating objects. So if you're an artist, it's basically the right brain which makes you draw those things. It prefers open-ended questions. It's free with personal feelings. Prefers collegial authority structure. Uh, important connectedness is important for that part of the brain. It's analogical compared to deductive reasoning. It sees correspondences, resemblances, and it draws on unbounded patterns clustered around images. So that's the theory. And somebody did an interesting survey, and I'll go over that survey and try to identify what are the basic uh, success and failure factors of certain large scale projects, and try to identify those factors and then try to map those factors with what are the factors which have to do with the left part of the brain and which are the factors which have to do with the right part of the brain. So we understand exactly what kind of thinking is required to have a successful project versus what are the reasons behind our failures when it comes to engineering system design problems. Okay, so when you said that we need a left mode and R mode combined methodology, these are the functions that people refer to when they use these terms L mode and R mode. But in a nutshell, if I try to summarize these things, all we are asking in system engineering is basically a combination of both knowledge and imagination. And how do we define knowledge? Knowledge is something which already exists. It's a memory of something which already exists. It requires convergent, deductive, and logical thinking. Imagination, on the other hand, is to create something which did not exist previously, but which can be realized through design and engineering, and it requires divergent, intuitive, and creative thinking. And that, again, is a debate in my department, in many other departments in system engineering, that the knowledge part is very well covered in university. So when you come to any university, basically they try to provide you with knowledge. You already have things out there that like you to know those things. What we fail, again, not NED, in general in university, what we fail to do is to teach students how to imagine, how to basically have a creative, way of solving things that may not require the knowledge that is being taught to you in the class. If you are a fan of Albert Einstein, he thinks imagination is more important than knowledge. Anyway, so here are those factors. And again, I understand that we do not have a lot of time, so I'll go over those things very quickly. So these are, and I've also put some references towards the bottom of these slides in terms of where these things have come from. So these are top success factors of some system projects that this group actually looked into. So identify what were the success factors behind these successful ventures. And this is the list that they came up with, and they published this thing. So there was a lot of user involvement. There was executive management support. There were very clear requirements. There was proper planning, realistic expectations, smaller project milestones, competent staff. They know what they were doing. There was an ownership. Everybody was, sort of had this sense of ownership of the project or the thing that they were developing. Everybody had a clear vision and objective, and people were hardworking and focused on those things. So basically, these are some of those factors that are common in all those success stories. On the other hand, the top failure factors were lack of user input, incomplete requirements, changing requirements, lack of executive support, technology incompetence. People were not aware of, or they were not users of the technology that they were using or proposing, lack of resources, unrealistic expectations, unclear objectives, unrealistic time frames, and new technology. New technologies, they were basically employing something that was so new that people really did not know the implications. So what somebody did, and interestingly, this work was done at LUMS Lahore. They basically compiled a list of all the failure factors from several different research work or work done at different industry organizations, and they compiled a long list of things which contributed to failure especially for software systems. So again, the list over here refers to factors which may be more relevant for software systems, but may not be that much. But again, if you look at those, they make a lot of sense for any project that you may be working on, civil, mechanical, electrical, or any. Uh, so again, if you look at those, hostile culture was one of the failure factors. If there is a bad news that you wanted to tell your bosses, it was always punished. Okay? Poor reporting structure. You kept people kept doing things, didn't report, didn't put them in writing. The success of project linked to the people. The people were only interested in making someone happy, regardless of what happens to the project. And it's something which happens a lot, not just in Pakistan, everywhere else. If people are only interested in making their bosses happy, the project suffers as a result. Overcommitment, decision-making escalation is something where you are making lots of meetings and decisions without doing much work. So whenever there is a problem, let's have a meeting, and then you keep on discussing things without much movement on the ground. Political pressures, technology-focused developments, ignoring the human, the lure of the leading edge. We want to have the cutting-edge technology, that kind of attitude. Again, these are failure factors. So these are not things which will guarantee you success. It's interesting to look at all of those and see how many of those we also sometimes do when we are part of some development needs. Complexity underestimated, inadequate consultations with major stakeholders, design by committee. So you have so many people involved in the design that nobody takes the ownership. If there is something wrong, I can always blame on the other. Technical fix for management problems. You have a management problem and you try to fix it by technical means. And it happens a lot again in every part of the world, especially in Pakistan. It's a management, it's a human problem, and you try to fix it by, can we computerize it, for example. Staff turnover, a lot of going and leaving, people are coming in, they are leaving the organization or leaving the team that is doing the job. So you don't have people staying for too long. Competency, not enough, people with the right qualifications. Exceeding deadlines, inadequate testing and training, communication problems and group problems. So these are all, factors that these people at LUMP came up with. If you compare or map them to, what causes these things, you will see that some of them are due to lack of right brain thinking and some of them are due to lack of left brain thinking. And that basically proves the proposition that we actually need both hemispheres of our brain to solve these complex large scale systems. We need both the left side of the brain and the right side of the brain for the kind of problems that nowadays we are facing. So that's what whole brain thinking, and that's what the system thinking. If you talk to people from system engineering, and they tell you that we need to have a systems thinking in place in our organization. It's that kind of a thinking, holistic. You don't just follow the procedure. You also need to sit back and look at the overall picture and try to identify, sort of an overall view of what is happening. It's considered both art and science. See what you are not seeing, because you may have an incorrect mental model, you may have lack of focus, you may have lack of understanding of the overall, all the factors which are affecting your system. You simply have not posed the right questions, asked the right questions. Maybe difficult questions to ask because of the hierarchy of your organization, but you need to ask those questions. Take a moment and simply reflect. Those are some of the things that people are now pushing when it comes to traditional project management and system thinking. So again, system thinking is about combining art and science to create comprehensive, cohesive, and creative designs. It's an ability to combine art and science, and it's basically this ability differentiates the star performance from the average performance. If you have both, if you know your processes, if you know your methods, and you can also be creative, you are guaranteed success in this field. Uh, Again, maybe all very abstract. I thought that I should give you some challenges that we are facing in Pakistan. The kind of problems that I consider systems problems that require both the left and the right brain to solve, whole brain thinking, art and science. This is a picture from Karachi. You see that traffic problem, another mess on the roads, the electrical grid problems that we have in Pakistan. I'm telling you, these are problems that not one single engineering discipline can solve. It's a problem that requires lots of different expertise. Uh, we need to bring all of them together. There are human factors, there are political issues, there are management issues, there are technical problems. We cannot solve any of these problems by only technical means. We need to bring all these things together. And that's why I think that we need to have system engineers. We must train some system engineers at our technical colleges or universities because these are the problems that are on our face. We see them, we face them on a daily basis. We have tried many fixes. None has worked so far. And the reason is that we are applying the linear analytical approach to solve these problems. And those are valid ways of solving things, but these are a different breed of problems. They are different animals. So you need to have different kind of engineers trained to solve these problems. Again, traffic problems. Can we realize the dreams of these people? Yes, technically it is possible. So many countries have, extensive urban transport systems, but in an environment like ours, we need a system approach to basically design and build these systems. Engineers working in their own area, civil, mechanical, electrical, may not pull this thing alone. So that's again a challenge that I pose to our young engineers who may still be, in the university being trained for future challenges. These are present challenges. Let's see if some of you can take these challenges and solve these problems. These are some of the references that I've used on these slides. So if you want to search for more details, you may go to at least one of these sources. I end my talk with this interesting quote from this, I think, 12th century preacher, St. Francis, who says, "He who works with his hands is a laborer. He who works with his hands and head is a craftsman." That's where the engineers, I think, come from. But then there is the third category. He who works with his hands, head, and heart is an artist. And what I'm preaching right now or trying to convey to you is that the new engineering problems require future engineers to be both a craftsman and an artist. If you have any questions, I'll be happy to answer them.
Mr. Anum? Hello, Mr. Anum, are you there?
I think someone is trying to ask. You can आप just जैसे भी जो भी सवाल करना चाहें
Can you hear someone, Dr. Abbas?
Hello?
Hello?
Hello, this is a student from LD University and I'm attending this seminar, so I have a question to ask the speaker.
जी, go ahead.
Yeah, hello. I am a student of final year textile engineering, sir.
Jay.
Sir, can you hear me?
Yes, I can. I can hear you. Please ask your
Sir,
question.
it's been a pleasure listening to you, and the seminar was really informative for me. But sir, don't you think there are some barriers we as an engineer or we Pakistani engineers face when we are up to implementing our systems or our ideology? Like if you showed some example of Pakistan or Karachi, that we have many we have been struggling to set it up Karachi because of that system of transportation and electric system. So
Mm-hmm.
there may be many Pakistani before me as well, and they may be engineers or they may be craftsmen or they may be artists. They might have come across ideas, many of them, many of the ideas to make them better and make Karachi better. But there are some political barriers and like barriers to to implement their ideas. So, sir, how do you like to support your program with this thing? Like, अगर कोई engineer इस बारे में सोचे and then he is up to implementing his ideas, तो वो किस तरह से मतलब करवा सके?
आपका नाम क्या है बेटा?
सर असलम जैन असलम.
असलम साहब, आपने जो बात कही है, I was trying to say the same thing. There are many obstacles, there are many problems. I think what is more important is that as engineers, we must realize that by ignoring some of these things, we cannot solve a problem. And I think that's what we are experiencing in Pakistan. There are so many, like you said, there are so many attempts, but you know, you don't see a solution. The cause of that is, is our approach towards these things. If as an engineer, if I, if for example, if someone asks me to solve a problem and I tell that person that, okay, this is a social issue, this is not my domain, this is not my jurisdiction, I'm an engineer, I can only do this. You may be doing your job, very efficiently, but you will not be solving the problem. So systems thinking is basically is trying to sort of train engineers to see the bigger picture. There may be problems, political problems, social problems, budgetary problems, many other things that traditionally, as engineer, you may consider not your problem. But all the system engineers or system engineering as a discipline try to teach people is you may ignore whatever you like, but then you are not solving the right problem. Okay, so we have this type 3 problem. You may be solving the wrong problem, and that's what has happened, especially, and again, I kept saying this thing, it happens all over the world. There are many interesting, ridiculous, attempts in United States of solving certain problems the wrong way. So it's not just Pakistan that I'm picking on. But you see some of those things a lot, unfortunately, especially in Karachi. Uh, as engineers, you cannot just, close your eyes from those factors which are affecting these things. So all I'm saying is that I understand your problems. I understand your sort of predicament that you cannot have, sort of control over some of the things. All I'm saying is the systems thinking tell us that ignoring those factors will not solve the problem. Unfortunately, that's how things are. So as engineers, we should be trained to look at the whole picture, regardless of whether we have control over all those things or not. So the message over here is a training of a new kind of an engineer who looks at the whole thing and comes up with a solution, considering all factors or parameters that affect the system's performance or function. We cannot be taught or trained by isolating, or carve out a small sort of a part of a problem and then solve it by technical means. It has worked, but it's not going to work for future systems because of the complexity that they involve. All I'm saying is that it's not wrong, but it's an old obsolete or becoming obsolete as we are going towards more human-centric, very large-scale, complex systems of systems. And I think that's happening in Pakistan. Nadra is being called for almost everything that happens in Pakistan. They are involved in elections. They are involved in crime, prevention. They are involved in disaster management. Nadra is a single organization. Why is it in all these different initiatives? It's a system of systems problem. You approach it from a system of systems methodology. The traditional approach will not work. All I'm saying is I agree with your comment. Unfortunately, we have some of those problems, but hopefully, one of these days we may be able to convince. The first thing is it starts always from our own institution. As an engineering institute, we should realize that we need to change our methods of teaching. We need to change our methods of training engineers. We need to train new kind of engineers, and that's where we should start. And let's see what happens, afterwards. Any other questions?
Sir, my name is Navidur Rahman, and I am a student of textile engineering at NED University. So my question is, whatever we learn here at NED University, being engineering student, when we see in industries there are machineries, there are machine, and when we will be employed there, we will have the management job. We wouldn't have the technical job like manufacturing of the machineries that we have studied about. Or when we see, we suggest any machinery, any firm or any industry that we should, instead of importing the equipment machineries from Switzerland or other Italy or other countries, we should manufacture at our own Pakistan, and we should even export it to the neighboring countries and other countries. They said that it's not possible in Pakistan. What we should do?
नवीद साहब, अगेन आप इस चीज को आप प्रॉब्लम बता रहे हैं. डेफिनेटली इट्स अ प्रॉब्लम, एंड अगेन इट रिक्वायर्स, आई थिंक इट्स अनदर ऑफ एन एग्जांपल जो मैं अपने आर्ग्यूमेंट के सपोर्ट में दे सकता हूँ कि हमारे यहाँ जो थिंकिंग है एट द लीडरशिप लेवल ऊपर, उन्हें भी मसलन एक सिस्टम थिंकिंग की जरूरत है. मसलन दे नीड टू लुक long term. They need to basically look at what the requirements are of a nation, not a sort of a single city or a single corporation or a single part of the government, and try to identify sort of a plan which in the next 10, 20, even 50 years would basically produce results. So मेरे पास यानी आपके इस कमेंट का कोई जवाब नहीं है कि हमें मैन्युफैक्चर करना चाहिए या नहीं करना चाहिए. If you look at the entire world, it's a very large system of systems. You cannot, in this new sort of world, the way it is organized, you cannot manufacture almost everything in your own country. You are dependent on some other countries, and in return, they are dependent on you. तो जो इशू है मेरे ख्याल में वो ये देखना चाहिए कि how can we solve our problems by employing, let's say, machinery or skills from outside, and what is it that we are contributing to the world. So what is our need? What is our expertise that we are contributing? So it's a new world. हम सब एक दूसरे से डिपेंडेंट हैं, और उसमें जो इम्पोर्टेंट क्वेश्चन जो आप रेज कर रहे हैं वो मेरे ख्याल में ये होना चाहिए कि हमारा शेयर क्या है इस नई जो 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 नया सिस्टम ऑफ सिस्टम. व्हाट इज इट दैट वी आर कंट्रीब्यूटिंग टू द फंक्शन ऑफ दिस एंटायर वर्ल्ड. ठीक है, तो हो सकता है कि बहुत सी चीज़ों के अंदर हम दूसरे लोगों से बोरो कर रहे हैं चीज़ें, लेकिन कुछ चीज़ें हमारी होनी चाहिए कि जो हम दूसरों को कंट्रीब्यूट कर रहे हो या वो हमारी चीज़ें बोरो हमसे कर रहे हैं. तो आपका पॉइंट सही है. बहुत सारी हो सकता है कि बात चीज़ों के ऊपर मैन्युफैक्चरिंग में बी दी आंसर. बात चीज़ों में हो सकता है कि बाइंग थिंग्स मे बी द राइट थिंग टू डू. I don't know the answer. All I'm saying is that it's a systems problem. Someone, or not just one person, lots of people, they need to sit together, plan for a sort of a long term. What we learn is important in the sense that these are our tools to solve certain problems. अगर आपको कभी मौका मिले कि आपको कोई प्रॉब्लम इस तरह की कोई ऑफर करे कि आप उसके लिए सोल्यूशन प्रोवाइड कर सकें, hopefully that will be the time when you will be using your skills. Until that time, I don't know what we as engineers can do other than try to identify the problems, try to come up with a solution. But again, आपने जैसा कहा कि हमें कोई करने नहीं देता. जब तक कोई करने नहीं देता, मैं जाहिर बात है कि हम लोग एज प्रोफेशनल इंजीनियर्स खुद से तो जाके आप नहीं किसी ठेकेदार का हाथ पकड़ के और उसको कहेंगे जिस चीज को ठीक करो. These are some of the social problems that we have in our society. किसी न किसी लेवल के ऊपर लोगों को गवर्नमेंट के अंदर पॉलिटिकल जो लीडरशिप है उसके अंदर लोगों को सोचना चाहिए. लेकिन अगेन एक टेक्निकल यूनिवर्सिटी के अंदर बैठ के मैं और आप इसको डिस्कस तो कर सकते हैं, लेकिन मुझे नहीं मालूम कि इससे ज्यादा हम और क्या कर सकते हैं. All I'm trying to sort of tell you is whenever you have the chance, whenever you are given a task in terms of developing a system, make sure that you do it right. And doing it right means, in my profession, having a sort of a more holistic approach than just finding things that I can do or I was told how to do. So the knowledge मेरे पास है that definitely would help me solve those things. All I'm saying is that in some modern day problems, you may have to also use creativity. That goes beyond your learned knowledge or acquired skills.
Assalamualaikum.
Welcome.
Sir, my name is Abdul Ghani. I am doing textile engineering. I am in second year.
Yes.
So sir, you emphasize on first of all that you are saying that in any university. So we emphasize on knowledge. We have to make we have to work on the imagination also. Okay. Oh, I think the first question is that so you need to put some of the suggestions or quotes whatever so to improve this era which is an important. And second question is that I am a textile engineer. So after 4 years I am getting degree of formal degree of professional degree of textile engineering. So I am not able to convert myself into a system engineering. It needs a it is constituted of different departments. So how can formally, professionally I be a system engineering? So need your comments on it.
अगेन अगर आप उस प्रोफेशनली फॉर्मली अगर आप एक्वायर करना चाहते हैं, मुझे पता नहीं है पाकिस्तान में कौन कौन सी यूनिवर्सिटीज हैं सिस्टम इंजीनियरिंग की डिग्री ऑफर कर रही हैं.
Okay, sir. I want to need you from there. Was the procedure and was the government doing it there? Was the act there to be a system engineering? I don't think in Pakistan there is any kind of department who is offering that kind of degree to be a system engineering. This is the modern world. And even if you go back there, they always need a system engineering to build something big. If a single person or single discipline cannot make something which is a requirement of today's world.
System engineering again, आप जिस कह रहे हैं कि गवर्नमेंट कुछ नहीं करे, I think it's a problem which every country is facing with right now. अमेरिका में भी बहुत नई जिसे कहते हैं कि इनिशिएटिव्स हैं, बहुत रिसेंट इनिशिएटिव्स हैं. इनकॉसी करके एक प्रोफेशनल एक बॉडी है जिसे IEEE इलेक्ट्रिकल एंड इलेक्ट्रॉनिक्स इंजीनियर्स के साथ इनकॉसी करके जो है सिस्टम इंजीनियर की एक प्रोफेशनल इंजीनियर्स की बॉडी है, which are basically trying to push certain things in both at policy level, at university level, education level. यूजुअली मतलब हमारे जैसे जो पाकिस्तान जैसे मुल्कों में होता है कि जब बाकी दुनिया में होना शुरू होता है हम लोग भी शुरू कर देते हैं. तो होपफुली मतलब है कि दैट मे कम टू पाकिस्तान वन ऑफ दीस डेज. पाकिस्तान में वैसे एक सिस्टम इंजीनियरिंग की डिग्री ऑफर होती है जो प्रयास करके जो पाकिस्तान इंस्टीट्यूट ऑफ अप्लाइड इंजीनियरिंग एंड साइंसेज इस्लामाबाद के करीब जो इंस्टीट्यूट, लेकिन उनका एम्फेसिस जो है वो न्यूक्लियर सिस्टम्स के ऊपर ही है. तो अगेन सिस्टम्स इंजीनियरिंग जो है एक टर्म है कि जो बहुत सारे यूनिवर्सिटीज में मुख्तलिफ किस्म के उसमें यूज होती है, मुख्तलिफ उनकी डेफिनेशन है. बहुत जगहों पे सिस्टम इंजीनियरिंग ओनली एग्रीकल्चर सिस्टम्स के लिए जो है वो डिग्री प्रोग्राम है. अगेन जो इन कॉफी के जो डेफिनेशन है सिस्टम इंजीनियरिंग की वो है कि जो मैं अभी आपको जिसे कहते हैं कि उसका एक ओरिएंटेशन देने की मैंने आपको कोशिश की थी। इन कॉफी की वेबसाइट के ऊपर आप जाएं, वहाँ पे आपको काफी मटेरियल मिल जाएगा। यूनिवर्सिटी की अगर लीडरशिप या लोग ऐसे यहाँ पे बैठे हैं कि जो साथी हैं एनईडी यूनिवर्सिटी के अंदर, दे मे लुक इनटू दिस एरिया एंड सी इफ दे कैन include some of those courses or some of those aspects in the regular engineering curriculum that we have in NID. क्योंकि अगेन सिस्टम इंजीनियरिंग ऐसा नहीं है कि एक दिन एक पूरी एक नई इंजीनियरिंग की जो है वो डिग्री ऑफर होगी। इवॉल्व इन सम यूनिवर्सिटीज इट केम फ्रॉम ऑपरेशंस रिसर्च डिपार्टमेंट, इन सम यूनिवर्सिटीज इट केम फ्रॉम इलेक्ट्रिकल इंजीनियरिंग डिपार्टमेंट। फॉर एग्जांपल एनईडी के एमआईटी में सिस्टम इंजीनियरिंग प्रोग्राम जो है it's part of the electrical and computer science department. Purdue के अंदर is part of electrical engineering department. So I don't know यूनिवर्सिटी एनईडी के अंदर कौन सा डिपार्टमेंट जो है उसके अंदर ये sort of capability exist करती है कि जहाँ पे कुछ लोग सिस्टम इंजीनियरिंग का इंटरेस्ट है उनका या उसमें उनका कुछ बैकग्राउंड है या as part of their research or their work they are solving systems problems. तो ये इन्हीं ग्रेजुअली आप उसको इवॉल्व कर सकते हैं। यूनाइटेड स्टेट्स के अंदर अब अंडर ग्रेजुएट डिग्रीज भी ऑफर होती हैं सिस्टम इंजीनियरिंग की। जो यूनाइटेड स्टेट्स के अंदर जो बॉडीज हैं जो लुक आफ्टर करती हैं डिग्री प्रोग्राम्स को, उसमें जो इंडस्ट्रियल इंजीनियरिंग का जो विंग है एट प्रेजेंट वो सिस्टम इंजीनियरिंग की डिग्री को लुक आफ्टर करता है। लेकिन इनकॉफी जो है जो प्रोफेशनल बॉडी है सिस्टम इंजीनियर की, वो कोशिश है उसकी कि वो एक सेपरेट एक डेवलप करें सिस्टम इंजीनियरिंग की जो डिग्रीज है उनको मॉनिटर करने का है, उनको एक्रीडिटेशन का जो है सिस्टम सेपरेटली फ्रॉम द इंडस्ट्रियल इंजीनियरिंग जो एग्जिस्टिंग तरीका। अगर आप लोगों के और सवालात हैं तो मुझे सिर्फ आप 2 मिनट अगर आप दे दें, मुझे सिर्फ यहाँ नमाज है कज़ा हो रही है, मैं पढ़ के वापस आ रहा हूँ।
Excuse me, sir. My name is Muhammad Abdullah. I am from Electronics Department.
आप मुझे 2 मिनट का टाइम दे सकते हैं, इसके बाद आप सवाल कर लें।
Okay, sir.
Just give me 2 minutes. I'll be back within 2 minutes.
The meantime, Ms. Paramal.
Yes, ma'am.
अस्सलाम वालेकुम। आपके पास जो ईमेल एड्रेसेस होंगे ना स्टूडेंट्स के,
जी जी बिल्कुल।
आप मुझे स्कैन करके किसी तरह भेज देंगे ताकि हम स्टूडेंट्स को कांटेक्ट करें। उन्हें डॉक्टर अब्बास को हम ईमेल एड्रेस भी दे देंगे कि उन्हें कोई क्वेश्चन हो।
बिल्कुल मैडम, ईमेल एड्रेस भी दे दूंगी, उनकी अटेंडेंस भी भेज दूंगी।
अच्छा, बहुत शुक्रिया। तो मैं आपका ईमेल एड्रेस अगर आप मुझे दे दें तो मैं आपसे कांटेक्ट कर लूँगी।
मैडम CSA@NEDA जिस पर हमारी करस्पॉन्डेंस होती है, उसी के थ्रू मैं आपको भेज दूंगी।
ओके, श्योर, बहुत शुक्रिया, थैंक यू।
थैंक यू।